Good morning, everyone. I'm Nassima Bouzid. I'm a machine learning engineer at Capital One, and I'm going to talk to you about kind of a mad scientist project that we undertook to try to see if we could generate differentially private synthetic data using an LLM. So for agenda, 4 parts. I'm going to just go over the problem in the financial domain that we are dealing with, that we are trying to solve with this approach, the specific approach that we're calling profile then simulate, and then I'll go over what worked, what broke, and then some lessons that are probably relevant for this audience. And yeah, that the hard part was not what we expected, so exciting. So first, the challenge here is we have hundreds of millions of transactions at Capital One. Really useful for fraud research, but due to privacy regulations, we cannot share that data. So with differential privacy, we have that the formal guarantee on the risk of privacy loss, and marginal-based synthetic data generators like AIM do a really great job of capturing distributions in lower dimensional settings. But as our domain size grows, so as we have more and more features, higher cardinality in data sets, like richer data sets, it becomes harder to capture those higher order marginals with high fidelity. And we have a lot of customer data, a lot of transaction data, and that's a really large joint domain that our marginal-based methods aren't performing as well on. So we asked the question, if an LLM already knows what realistic financial behavior looks like, can we seed it with short, differentially private user personas, so kind of summary statistics about users, and have that generate realistic transactions that capture that user's behavior. So can we get the best of both worlds? Can we get the formal guarantee from DP and also get realistic outputs from an LLM? So here's our approach to try to do that. We're calling it profile then simulate, and this is what it looks like. So I'm going to talk about on the left-hand side, this is profile then simulate. And there's 2 phases. So first we started with 2,000 users and 24 million transactions. And we took out our test set. So we took all of the transactions for 400 of those users and set them aside, did not touch them. For 1,600 users, we took all of their transactions and we distilled them down into user personas that captured the behavior. And then we took that data set, that summary statistic data set, and then ran it through AIM to have a differentially private version of those user personas. And so all of the privacy budget was spent there. Then we passed it to PersonaLedger. And for PersonaLedger, that is an LLM-based transaction simulator that some of our colleagues at Capital One built. And it's a Llama 3.370B model in this closed loop with a rule-grounded engine that enforces financial constraints like balance limits and payment schedules. So what we care about for transaction data and making sure it's realistic transaction data. But the LLM is never seeing real data. The LLM is only seeing these differentially private user personas that have been distilled from the transaction data. And then we compare them. So what I just talked about was profile then simulate. So that's this 2 phases of first we take the raw transaction, we distill them, we protect them with DP, and then we use PersonaLedger to generate realistic transactions from those personas. On the right-hand side, so direct synthesis, this is our baseline that we compared it to. So in this case, we took those raw transaction records from the users in the training set, and we ran it directly through AIM to generate differentially private transaction logs. And then at the bottom, compared the 2 data sets, synthetic transaction logs, one from PersonaLedger and then one from the direct synthesis. Cool. And here's our evaluation setup. So we followed the train synthetic test real protocol, and we trained an XGBoost fraud classifier on both of the synthetic data sets, and then tested them on 100,000 real transactions from the holdout set of users, those 400 users that we set out. It had about a natural fraud rate, so it was a realistic problem that we could solve with that XGBoost classifier. And then we did this across three privacy regimes. So we had aim at epsilon of 1, 5, and 10 so that we could see how the performance of the model varied across those privacy regimes. And the way that we evaluated it was using AUC to figure out how well the classifier was performing on that downstream fraud detection task. And then we looked at fidelity of the attributes using total variational distance. So those two dimensions there. Okay, so now I'm going to show you what we found. Don't want that. Okay. So here, what we're looking at are the results of utility. So this is the performance of the fraud classifier on the downstream task of fraud detection. In orange is PersonaLedger, and then blue is the baseline of direct synthesis using AIM. And so there is a non-monotonic relationship with the privacy budget that we found that was interesting, because if you look at epsilon 1, pretty strong protection. The PersonaLedger classifier was already pretty reasonable at like a 0.7 AUC, but as you go with epsilon equals 5 and 10, we saw that epsilon equals 5 actually performed worse, which we didn't expect. So it looked like there wasn't a relationship between the epsilon and how well the model was performing, and that told us that something was probably happening with the LLM, because that was an unexpected relationship there. And so we wanted to understand, okay, if it's not coming from the DP noise, it's something inherent to the model. Is that something that we can look at and fix there? But if you look at the direct synthesis, that's pretty reasonable performance across epsilons of direct synthesis on the raw transactions. And so next. This is fidelity. So we are looking at the one-way and the two-way marginals, total variational distance of the marginals, comparing the features across the different privacy regimes. And here you can see it's pretty high, so lower is better here, the total variational distance of the feature marginals. And for PersonaLedger in orange, this is showing us when we actually look at the features that the distributions are not matching what we are putting into the LLM. So when we use direct synthesis, the feature distributions are matching the distributions that were input, but using PersonaLedger, they're doing something completely different. So that was really interesting, and we wanted to dig further into that. And so we did a root cause. So we looked at the specific attributes to try to figure out where is the LLM breaking down. And what we found was when there are demographic features, so like whether a customer is retired or not, there was a pretty big gap between what we saw in PersonaLedger and the direct synthesis. So in the real data, about 50% of the customers were retired. The LLM decided that 80% of the customers were retired. So there are these inherent biases in the LLM that were being persisted, and it was ignoring the input that we were actually putting into it to generate the transactions. Similarly, for time of day, the transactions that came out of PersonaLedger clustered during business hours, like 9 to 2 p.m., and those night and evening patterns that we saw in the real data weren't preserved. So the LLM had decided that nobody makes transactions outside of business hours, which we know is not true. What did work were lower cardinality features, so binary features, gender, those actually matched up pretty well. So when we looked at the marginals and the total variational distance, those were pretty low. Our conclusion there is that really simple distributions seem to be transferring when we do this profile, then simulate approach, but complex or non-stereotypical patterns, things that the LLM thinks are wrong, are drifting. And so that is the thing to try to address here. So go there. Come on. Oh, it doesn't want to move. Okay. This is the main takeaway. So the bottleneck here in this experiment turned out to not be privacy, it was the LLM faithfulness. And more epsilon was not giving us a better synthetic data set because the LLM was ignoring us. Okay, so some like practical recommendations based on that. A couple lessons that we came up with or that we found were direct synthesis works really well when you have lower cardinality, like a more tractable problem in the data set. So you have fewer features, you want high fidelity, then the direct synthesis worked well. And just to note that our direct synthesis, the transactions had about 12 features. So this is an ideal problem. And it makes sense that it performed so well. And so we wanted to kind of have this ideal problem to compare profile then simulate again to just see how well it performed, how poorly it might do. The LLM approach is different because, like I mentioned before, we have tons and tons of customer data. That's a really high dimensional data set, and we want to be able to capture that information to generate synthetic transactions. So this LLM approach, I think, is still promising. And when in cases where direct synthesis would collapse, you have all of those features, and you don't have the behavioral realism like we would expect with transaction data, we could do this LLM approach. The other thing that I just want to call out is like measuring fidelity and not just utility. So not just the performance of the classifier, because like I showed you for epsilon equals 1, it actually looked pretty good for profile then simulate. But when you drilled down into the total variational distance of the features, you could see that the LLM was actually not taking the information. Really quickly, I want to also plug, because there's a lot of people working and encountering kind of similar problem. Some of us went to iClear, and there's some really interesting approaches that people took to solving this problem. Just briefly, and I put that up there. So it is really interesting, and there are solutions that we can try to improve this profile then simulate architecture. But just to wrap up, profile and simulate does seem promising. It's an area of active research. Like there are ways that we can try to get the LLM to actually listen and take in that information so we can generate realistic transaction data. But interesting, and we didn't expect that the problem was going to be the LLM faithfulness. That is what I've got. Thank you. I take any questions.